Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good evening, everyone. My name is Jay, and our team's project was on the NYC taxi system and looking at its efficiency. So just as a quick question, how many of you have taken a cab in NYC before? A yellow taxi, specifically. OK, so most of you. The taxi system is a huge part of New York City's transportation. It allows people to get everywhere, work, airport, or just hang around in the city. If you go outside right now, you'll see about, I don't know, maybe 20 taxis going in all different directions. And each cab is going to its own destination, carrying a passenger. Each cab has its own story to tell. But imagine if you had a bird's eye view of all the cabs in New York City, and you were able to see where every single cab was going, who they were picking up, who they were dropping off, what they're doing afterwards. What would we be able to learn from that? And so if we had that data, we would be able to understand how people move throughout the city. So we would understand where people go, where the hotspots are, and where people in our city, how they're living, what they want to do, all the different activities that they do. We would also be able to zoom in from the top and go down to specific drivers and understand what roles drivers play in the taxi system. Are there good drivers? Are there bad drivers? If I'm late to work, do I catch this driver or this driver? Is there any correlation between drivers and the efficiency of taxis? And last but not least, how can we use an overview of the system and driver information to improve the overall taxi transportation system? Now, the best part is that we have access to the 2013 yellow taxi dataset. So this is every single trip that took place in 2013, every single trip. So if you tell me where you were on New Year's Eve on 2013, I can find the exact trip, how much you paid, and I can tell you a lot about your story. But we won't get into that. We chose July 2013 just as a month to do our analysis on. The data set's huge. We have about 13 million rides just for 1 month. So that's what we could fit on our machines. And each trip had information such as a driver ID that was anonymized. It's called hack license over there. The drop-off pickup time, the drop-off pickup location in coordinates. And it had the fare amount, the metered fare. We also had information such as tips, taxes, the number of passengers, and other information that was really cool. But just having this information was enough for us to do our analysis. And so with any large data set comes cleaning up the data, looking for nonsense in the data. So one nonsense we had were some really bizarre coordinates. So taxis started off in New York City, and they ended up in the middle of the United States, in Virginia, Texas. We even had one taxi that ended up in Antarctica, somehow. I don't know how we got there. And we're still looking for where that taxi is today, but we have no idea. Keep you posted. And then we had drivers that were somehow able to clone themselves. So if you look at this driver's information, these are his trips sorted by time, by the pickup date time. If you look at the two highlighted rows, he's picked up a passenger at 9:56, and then he dropped off the passenger at 11:04. If you look at the next row, he picked up a passenger at 10:29 and dropped the passenger off at 10:44. Now, is this possible? By a show of hands. One person? OK. Maybe. So the way this works is when you hit start on the meter, you record the start time for your trip. And then when you hit the meter again, the trip's over. So this would only be possible if the same cab driver was driving two cabs at the same time. So that tells us that there's some nonsense in our data, and we threw this out so that we can work with more reliable data. And last but not least, we had some fishy drivers who were making a lot of money in a very short time. So we had drivers who drove for 1 minute or less and made $400. So what's going on? We have no idea. But now that our data is clean, we're able to begin our analysis and start by answering our first question: what is the flow of our city? And so Abe will talk about that.
once we had the data clean, we first wanted to take a very 30,000-foot view of the city. Basically, as Jay mentioned, the taxi system is a major mode of transportation that people in New York City use every day. And we wanted to look at how people move about the city. Specifically, we wanted to see, are there trends in how people move about the city? Do these trends vary over across time and neighborhoods? And can we make generalizations about it? So, but first, to be able to do that, as Jay mentioned, the data comes recorded in geographical coordinates, and we had to convert basically 10 million geographical coordinates to neighborhoods so that it should be more natural to reason about them, basically to humanize the data. So for that, we use something called shapefiles, which are basically a long list of geographical coordinates that define these neighborhoods, and we use that to translate these 10 million pairs into, for example, that geographical coordinate up there into Chelsea. So once we had that, we were able to basically analyze the flow of the overall system. So to measure the flow, the easiest way to think about it is that we score neighborhoods based on their passengers that come into the neighborhood and passengers that go out. For each incoming passenger, they score a point. For each outgoing passenger, they lose a point. And the total is basically inflow minus outflow. If it's a net positive, that means that more people came in. And if it's a net negative, more people went out. And we do this for every hour. We restart the score, and at the end of the hour, we check again how many people. So this is New York City at 12 a.m. In the next slide, you'll see this as an animation, 18 seconds over the entire day. And you'll basically see that Midtown is kind of like the heart of New York City. And basically, over the day, it's kind of like a heartbeat where, so this is early morning. You can see that Midtown is empty. But then in the morning, you can see at its brightest, at 7 a.m., it's about 6,000. And then as the day progresses, people start flowing out of Midtown and into the other neighborhoods. You can see that Uptown gets really hot. This is about the negative 30,000 score. And the same pattern repeats itself every day. And other interesting parts to look at in this data is that outer boroughs, such as Staten Island and Brooklyn, are mostly stable. Slightly orange means more people are coming in, not as many people going out. But the closer you get to the city, the more variation you see, the less traffic between the city and these boroughs happen. And a third part that is very interesting to look at is basically the airports. So this is JFK, this is LaGuardia, and you can see that basically for most of the day, more people are going out of LaGuardia than are coming in. But early morning, watch what happens. It becomes bright red. Basically, not too many airplanes land early morning, so not too many people take taxis out of the airports, but many people come in. So that's why, so you can see that there's like at some point it gets a score of 1250 or even more net inflow. And once we had that data, we wanted to look at specific neighborhoods. We wanted to see do different people move about differently in the city. So what we did was we split up the data by neighborhoods. And so, for example, I come from Williamsburg, and there's a lot of hipsters living in Williamsburg. So I was interested to know how do people use the taxi system to move about. So this is morning on a weekend, and you can see they hang out basically in East Village and locally. But watch what happens during the weekday at the same time. You can see a lot of them work. They always hang out in the airports. And the same thing happens for a different thing happens in the afternoon. This is 5 a.m. on weekends. You can see they hang out around locally, Bushwick, Greenpoint slightly. But then during the week, you can see that it's much more spread. They're also going to Midtown, and there's also airport activity. So, but this is just one neighborhood, and this is just one story out of a million possible stories. The city is a multifaceted, multi-layered, I guess, storybook. So we built a tool that helped us basically explore this, where you can choose a neighborhood, time of the week, hour of day, and it shows you basically what are the most popular destinations given a pickup neighborhood. And once we had that 30,000 view, 30,000-foot view of the flow of New York City and the taxi data, we wanted to zoom in and go to the level of individual drivers and see if we can find anything to reason about them. And for that, I'll introduce my teammate, Mariam.
All right, thank you, Abe. Good morning, everyone. Good evening, everyone. Okay, my name is Miriam, and after having a high level of where people are going and where people are coming from, now I will introduce a new concept, which is about driver's efficiency. So in this section, we want to answer two main questions. The first one is, how much do drivers' earnings vary? And the second one is, how much skill is involved? In other words, can anyone be a cab driver? Well, the first step to answer to that question is just to define what driver efficiency is. In our case, it is just the ratio between the total meter fare, that is the total amount of money a cab driver is making, over the total work time. So in order to determine the total meter fare, all we had to do, according to our data, since we already have the fare amount for each trip, is just to do the summation for each driver, his fare amount for the entire month. But how about getting the total work time? Our data is just giving us the total trip duration in seconds, so the time that the driver is spending with a customer. But how about the total time that he's been working to make that much money? That's why we have to introduce a new concept here, which is about shift identification. So in this first plot, we randomly selected 50 drivers, and we look at their pickups and drop-off activity during a week in July. So these black dots are just their activities, they pick up and drop off activities. So it's like getting one customer and then having trips in between. So what we can see here for the entire week is that they're not working every single day, every time, and every moment, which is impossible. So they are having obviously some pauses, and then they go back to work. So our objective here is to know, is to generate for each driver, for all of the drivers, this working period, so that we can effectively calculate the efficiency. So one way to do it is to look at here a distribution of drivers in the y-axis, and in the x-axis we have the downtime period. The downtime is nothing else but just the time within each trip, which is the time that drivers are spending to find another customer after they drop off their previous customer. So, and according to this histogram, after a 6-hour period, you can see that there are no pickup or drop-off activities. Therefore, we found it reasonable as a rule of thumb to say that if you don't see any pickup or drop-off activity for the drivers for at least 6 hours, then we consider that as the end of his work time period or his shift. And then he's going to start a new one later on. All right, so is that 6 hours break accurate or not? Plausible or not? Guess what it is? Yeah. Well, this means that these red lines are just telling us that the time that they've been working, and it tells us that our 6-hour rule of thumb is kind of fit very well for the drivers that we've been looking in this picture. All right, so now that we have a better understanding of driver's efficiency, how we can compute it, we can move on our modeling stuff and our predictions and eventually results. So here we did a regression model, and we include these features. The first one, and the most interesting one, is the driver's ID. As Jay mentioned, we had as the hack license, followed by the start hour. Then we have this variation is weekend or weekday. But also we also joined one information, which is about weather, and the most interesting one was the precipitation. We also included the average trip duration and distance. And we also have, at last but not least, the percentage of all pickup and drop-off neighborhoods. All right, so here we can talk about the time of day effects. So in this interesting plot, what we can see in the y-axis is the average efficiency of the drivers. In the x-axis, we have the start hour time. So for the red distribution, we're seeing the average efficiency of the drivers according to their start time, and it is about the weekdays. So that's what we're seeing. And the blue one is doing the same thing, but just for the weeknight. So one thing we can notice is that the weekday tends to be more efficient until about 19 to 17 p.m. 17, because we can see that the weekend is kind of winning the game at those times. So what we can say is, and also these dots means that more drivers start their shift at those times. So the bigger the dot is, the more drivers we have starting their shift at this particular time. So what this graph is basically telling us is that the best time for drivers to start their shift is around 3 p.m. But interesting thing is that the drivers, even though this is showing that it's the peak time for them to start working so that they can be more efficient, most of the drivers do not start at a time. Okay, and now we can talk about some results that we get. All right, so in average, based on our model, drivers are making $30 per shift hour. And this distribution is showing us that those average drivers fall into this range. But interestingly, we can see that extreme drivers are making $10 less or $10 more consistently each shift hour period, which is a really huge point because we wasn't expecting that drivers was having this variation of earning, So this was more than we expected because in fact, with this random distribution and random distribution of the driver's earning, we can see that if their earnings was due to chance, then the extreme drivers will make at most $5 more than the average, but that amount doubles with our actual model. So yes, drivers' earning vary over time, and that variation is not due to chance. So to answer that question, can anyone be a cab driver? Of course, if they want to, but there are some skills that they really need to practice, like knowing where to pick up a customer, at which time, to think about the weather effect, and at which neighborhood to pick up their passenger and at which time. So now that we have a better understanding of driver's efficiency, I will let my colleague Fatima tell you about how can that increase the overall efficiency of the NYC taxi system in general.
All right, thank you, Mariam. Hello, everybody. So now after we have that general view of people where they are going every day and where they are coming from, and we have like a global view of what's make a driver efficient more than another driver, how can we use all this information to improve our system? So to answer that question, so we had to do some calculation, and one of the calculations that we did, we just had to count the number of trips that happen from a neighborhood X to a neighborhood Y. And this is one example of the data that we find. So if you see here, those are the trips that happen between the Port Authority bus terminal and the Rockefeller Plaza. If you see here within 5-minute windows, you see 6:25, 6:30, 6:35. Those are the number of trips that happen from that place to this specific place. For me, it's like incredible. This is like amazing how you see like people have like the 22 trips happen at the same 5 minutes blocks have at the same time. So next time when you're taking a taxi, you have to think like at the same time, at the same 5 minutes blocks, there are too many other people are taking the same taxi to from the same place to the same place. That's amazing. So we use this information to introduce the solution, which is the carpooling. So if we see that people are going from the same place to the same place every 5 minutes, so we can use carpooling. So carpooling has great benefits, which people don't mind now or not think about. So one of the benefits are you can save your money. So if you share the same car with other people, so you get to divide the amount, and more people you have in the car, that means more money you save. At the same time, you can save the environment. So when you cut down the number of the cars on the road, so you cut down the carbons that goes to the air. At the same thing happens to reducing the traffic. So the less cars we have in the road, the less traffic we can reduce. So for us to apply the carpooling to our data, we assume that people are willing to share the cars first and wait at least for 5 minutes. I think like this is significant numbers. Like people here I think most people can wait for 5 minutes. Then they can walk for a block, and they can share the destination, which is 1 kilometer, which is 4 to 5 blocks radius, and they can travel across neighborhood. So using all this assumption, how much really we can save? So we apply our assumption, which is 5-minute waiting, working for a block, and sharing the same destination with 4 to 5 blocks radius, and we get the top 25 hotspots. And not surprising, JFK is number 1, LaGuardia is number 2. Penn Station has like sharing the number 3, 4, and 11. Why? Because if you see here, Penn Station has like 3 exits. So they have like people take taxi from different exits. That's why we have like 3 hotspots. So generally speaking about the list, most of the hotspots are like transportation places, and other hotspots are like more culture sites. So we were talking about like what's hotspot, but we want to see like numbers, how much we're gonna save exactly. So that's why we use with the carpooling. So we had to do some calculation. First thing that we did, we calculate how many cabs needed. So we took the total passenger that we had, and we divided by 4. You're gonna see what's 4. So 4 is the number of people can fit to the car, and we had like 92% of the cars were like 4 passenger. That's why we had to divide it by 4. So, and the total fare paid was the average fare multiplied by the mean cabs. So this saved us like 700K trips, which is 5% of the total, and saved us like $10.1 million, which is 6 of the total. We've been like very strict about our assumption. As I told you, 5 minutes, you have to talk 1 minute. But if we were to be more relaxed about that and switch it to like 6 minutes and maybe walk for more than blocks, so we can improve our system to 14%. So to conclude our talk, so we had like 3 big questions to answer. The first question was, can we understand the traffic in the city? Yes, we had like a big view of where people are going every day and where they're coming from. And next question was, how can we understand driver analysis and how efficiency they are? Yeah, using our data, we can see that it's not the efficiency of the driver is not due to chance. Some people are more efficient, some people are less efficient, and it's due to their skills. And the last question was how we can improve our taxi transportation system. And one of the solutions was the carpooling, which can make the system more efficient, save us the money, and save the environment. And that's it. Thank you. If you have any questions.
So I just have a question. How did you get data for the passengers? Do the drivers enter the data? Like, where's that coming from?
About the passenger?
For the number of passengers.
Oh.
You guys mentioned that you guys knew the number of passengers for.
Yeah, we get it from the data frame. We had a column for the number of passengers that were in the taxi.
I think it's manually entered.
That's manually
Yeah,
entered.
by the driver. Yeah.
Thank you.
Yeah.
So you guys showed that there was like huge variation in terms of like the amount of money that drivers got, right? Did you look to see like how much of that variation is explained by like factors, because drivers probably have like certain shifts or something, right? So I'm just curious.
So our model that we had included a lot of factors: start hour, the neighborhood's precipitation. And so the way the regression model works is basically it accounts for those factors, and it gives you coefficients for how strong drivers are. So it does account for the factors other than just a driver.
even though, as I mentioned while I was explaining it, is that the driver's ID is the most interesting feature. It's not the only one, but it's the most important part that we need to do the analysis. So as Jay mentioned, we have other features, and then we even join another information from another data frame, which is the weather. So it's not only the driver, even though it's the most important feature.
So at some point, you compared the distribution of driver wages to a randomized distribution.
Right.
But the kind of random distribution would greatly depend on what assumptions you make. So I'm wondering, how did you actually compute what would happen by chance distribution?
So, can you go back please to that slide? Oh, yeah. So basically, the main difference between these two distributions is that for the random one, we just shuffle the hack license. So what we did, okay, we just shuffle the hack license. So we randomly assign efficiency to any drivers to see that if, again, the driver matters a lot in our predictions. So that's why we just have this small variation. It was just due to chance, just a $5 in each side, -5 +5. And then in this one, we just considered, like for all drivers, we give them the actual efficiency value. So that's the main difference.
So maybe piggybacking on an earlier question, if I were going to become a taxi driver, could you give me any tips on how I could, sort of be the most efficient?
Oh yeah, sure. Based on our model. Can you go back to the first? Yes. Oh, no. The features. Okay. So, of course, we need you. That's why we have the driver's ID over there. But then we have other features that. So we had previously a list of 50 features, but then we was doing some combinations to see which of those features are more powerful and can make you more efficient. So one of them was the start hour. Can you go back? Was the start hour. So here we were seeing that even though most of the drivers tend to start working during these times, but in order to increase the average efficiency, they should start from at least, start at around 3 p.m. So that's one feature. And another one is also to look at where you're going, depending on if it's a weekend or weekday. So for the rush hours, I was talking about the mornings in the weekdays and the night for the weekend. And also look at if it's raining or not, because if it is, people are more likely to take cab, and so the drivers tend to make more money in that period. And also you have the average trip time and duration, but also this is an important fact, the neighborhood. So where you hang out at what time, and depending if it's the weekend or weekday.
So for you to be an efficient driver, you should just start at 15 p.m., and be a night driver and work in the weekend.
Does the amount of tips the drivers get vary a lot? Is that why some make a lot more money than others, because they get bigger tips? And how much do people tip?
So first of all, we had cash tips and credit card tips. Credit card tips were recorded and cash tips were not. So for the credit card tips, we had some ridiculous numbers like $300, $400 tips. So we also had this column that was called rate code. A 1 meant that it was a standard metered fare, and a 5 meant that it was negotiated. So say you got in a cab and you say, hey, follow that person. I'll give you $500. That could have been the case for a couple. So, but generally speaking, we had, after we cleaned out our data, we had tips that were more sane, $80 or less. I'd say 80. I saw a couple of 80. Yeah. But
we didn't include in our model. The point is that we didn't include it in our model.
yeah, but we did not include tips in our fare amount because they're subject to the customer and they were not recorded for cash. So.
Could you go to the slide where you estimate your savings really quickly? Like yeah, this one. And so you're saying we would save $10.1 million. And so for taxi drivers then, would that mean they'd be making less money on whole as an aggregate too? Does that make sense if I'm understanding it correctly?
I mean, like we just seen like how we improve our system using the passenger side. So they are the one who used our system, so they are the one who can make it better. So we just had the view from the passenger side, not from the driver side.
Right.
But I think like the city tried before, and they had like they choose like a specific drivers to work in a specific spot, and they had they make like the amount of the fare more, so the driver can win too. So it's a win-win equation. Yes.
So I might be slightly off on the dates, but I think that your data is from around the time that New York introduced these green taxis, and I was wondering if you could use your data to say anything about, how these green taxis change the flow of people in the city.
So do you mean, so we didn't actually do any analysis on the green taxi because there were a small percentage of the overall taxis in New York City. And we chose 2013, which was, I think, the first year that the green taxis came, because 2013 had information about driver licenses, anonymized. If we wanted to work with 2015 originally, but then we would not be able to do a driver analysis. So for that reason, I guess we were not, well, for time purposes, we cannot do green taxi analysis.
Yeah,
but
and we choose July as the month to work with, and the green taxi was started at August, so we're like a month off. Yes.
The improve the system by 14%, is that combined with the trips and the amount saved if you lessen the restrictions, or it's one or the other?
The 14%.
Yeah.
So if we not restrict our assumption, so we can. I'm not sure which one we can save. Mm-hmm.
The 14% specifically is cab saved, which is actually a money which is always higher than cab saved, but it's not combined. It's just the total money saved for passengers.